Today's session, we had a look at capacitor charge discharged last week. Okay, this week we're going to have a look at the inductor situation. So then we'll have covered the theory around the two experiments you're going to do, the assignment, the following 2 weeks. So the remaining 2 weeks up to Easter, we'll get that practical work, so you've got all your results done and dusted, and then you'll be able to write your assignment reports. So, on the basis of covering the other half of the theory around the practical experiments for the assignment, I'm going to have a look at inductors today. What I'm going to do is do a little bit of a experiment up the front here with a coil, and get some results for AC and DC current in a coil, and then the rest of the lesson is around explaining why those results happen in terms of the difference between a coil in an AC circuit and a coil in a DC circuit. Alright, so up the front here I've got a coil of wire. It's just a simple coil of cable, both ends out, so we can take measurements off it and pass a current through it. What we're going to do is measure the resistance of the coil, calculate using Ohm's law what current we expect to flow for a given applied voltage. Then what we're going to do is actually apply those voltages and take readings, see what the differences are, and then, like I said, the rest of the lesson is around explaining why there's a difference. Okay? So I'm going to pause the video now. We'll do the experiment, record the results, and then talk about it afterwards. So, let's have a think about those results. Anyone got any ideas what's going on and why the current here is significantly less, nearly half of what it is? Yep, it is. It's around the magnetic effect of a current flowing through the coil. Okay, but more about why is it? Because we're making a field with the DC. So why is it different for AC? Yeah. So what's going on then, Jake? Do you think? Can you remember it from any other previous learning? No? Last thing I want you to do is, using the voltages applied and these currents, work out the DC resistance and the effective AC resistance. Anyone remember what AC resistance is really called? Impedance, measured in ohms. Okay? So, using those figures, work out what the DC resistance is and what the AC impedance is. The remainder of the lesson is around the theory of what causes that to happen. Yep. And the experiment is around you using AC and DC current on a coil to determine the inductance of the coil in henries, which we'll talk about in a minute. Okay? And it's quite an accurate way of measuring. It gives similar results on the coils we use to what Chris gets when he uses a Topwood LCR meter worth over £1,000. Okay, so it's a recognised method of finding the inductance of a coil. So, electromagnetic induction. Two laws governing this. First of all, Faraday's law. A voltage is induced in a circuit whenever relative motion exists between a conductor and a magnetic field, and that the magnitude of this voltage is proportional to the rate of change of magnetic flux. It's about changing magnetic flux and how fast that's changing. It will induce a voltage in a piece of wire or in a coil. Okay? Secondly, so this induced voltage in a closed circuit will cause a current to flow. Lenz's law states that the direction of an induced EMF and therefore current is such that it will always oppose the change that's causing it to happen. So it's opposite direction voltage induced to that which you're applying. So it kind of holds back the current, right? And that's where this comes from. That's where this extra resistance to current flow comes from, all right? But a bit more work needed yet to understand that fully. So there are the two laws, okay? So, electromagnetic induction, the situation with DC. If we pass a DC current through a coil, the conductor produces a magnetic flux around that conductor, and they form an overall field. If we pass a current through a single conductor, I'm going to draw two conductors looking at the end of them. In that one, the dot indicates that's the current arrow coming out and hitting Kyle in the middle of the forehead, and that cross means current going in. Anyone remember how we determine the direction of magnetic field? That's motion and motors and generators. Fleming's left hand and right hand rules. But good to hear you remember it. Corkscrew rule, remember, or screw rule? Which way would we have to turn a screw to make it come out of the board in that case? That way. And I'd have to screw clockwise that way. Yeah. So if we get, the issue is, listen, quiet down please, you've got a lot to do in this lesson. If we get two like that together, and put two crosses together, what tends to happen is we get a complete field all the way around the outside. They combine. Yeah, and actually there is a force acting to pull those conductors together. So where we've got all the current coming in the same direction at the top here, we get a field, and a field at the bottom. Effectively, you create a north and a south pole while that current is flowing. That's the DC situation, and the current will be steady. Okay, we can switch the poles around north and south by changing the direction of the current, and so on. There will be, like there is with a capacitor, a transient period, a charge period where that magnetic field builds up and where it falls away. There's a time constant, works very similar to that for the capacitor. Perhaps if we can fit it in, we'll be doing that after Easter, charge and discharge of an inductor. But it's got a similar repeatable pattern to it. It's just that generally the time constant's much shorter for an inductor. Yeah. No. If you think about this coil, Jake, the point I'm trying to make is, at the top here, if we looked at the conductors coming around that coil like that, all the ones at the top would be dots, wouldn't they? Coming out of the board. Yeah, and all the ones at the bottom would be crosses going in. So they combine to make that whole field. Rather than just going around individual conductors, they combine and make one big field. Alright? Well, that's the theory anyway. Yeah? Because you wind in a coil like that. So if you look at the top, they're all coming over the top, and the bottom ones are all going in. Remember, that field is completely around that coil. We're only in 2 dimensions here, but it's a 3-dimensional field. Alright? So, electromagnetic induction, oh hang on, just go back to that previous slide. These points that are important here. The strength of the field can be increased by increasing the number of turns on the coil, by increasing the current, or by adding a ferrous or iron-based core into the middle of the winding. So you actually improve the magnetic circuit. Okay, so that's what the strength of that field will depend on. On this page, Michael Faraday discovered that if a magnet was moved in and out of a coil, it induced an electromotive force, EMF, or voltage across the coil, and therefore a current was produced. So if we take this bar magnet and we move it inside that coil, we'll induce a voltage in one direction. If we take the magnet out, we'll produce a voltage in the other direction. That voltage will only be there whilst the magnet is moving. As soon as you stop, as soon as there's no relative movement or change in that field, the induction stops. Yeah. If we switch the magnet around, then the direction of movement to direction of current will be opposite because we've changed the poles around. Okay? They magnetize the material. So they experience a really strong, they choose a material that will hold a magnetic field, and then they magnetize it with a really big electromagnet, very high field. So, yeah. I don't want to go, that's really outside the scope of what we want to do. But you choose a material with a really high, what's called magnetic hysteresis, that once you've magnetized it, it will hold that magnetism. Yeah. Well, they're not natural magnets as well. It's not an area of expertise for me, but yeah, all right. So, you will also get an EMF if you keep the magnet still and move the coil. It's a relative motion between the two objects. Okay? Magnitude of the EMF produced can be increased by adding more turns to the coil, increasing the field strength of the magnet, or moving the magnet or coil faster, the velocity of that movement. What you must be sure of is that these lines of force must cut across conductors, not move along them. That will create nothing. It's cutting across a horizontal conductor. So if we look at a conductor here going into the board, this field has actually got to cut across that conductor in movement. If we move it along the field, we'll get no induction. So that 90 degree is the best movement across. Okay. Is everybody happy with that so far? Basics of induction. Pass a current, we get a magnetic field build up, and if we move a magnet near a coil, we get a voltage induced. You're like, if that's a conductor, Jake, looking in the board, yeah, and you've got this magnet here with its field coming out this way, if you make that field cut across that wire, or you make the wire cut across the field at 90 degrees, you'll get induction. If you cut at an angle, you'll get less induction. If you move it along that field, you'll get nothing. No, you. What transformer? Oh, why you should keep the cables separate? Yeah, sort of. It's all of this is why if you look at extension leads that go on reels, if you look at them carefully, they'll say something like 13 amps completely wound out. If you have them wind up maximum kind of 3 amps or 5 amps. One, because of the heating effect, but two, because of the induction causing even more heat. Yeah? Okay? Right, so if we put this coil in an AC circuit, what we've now got is we've got a voltage that's doing that, and we've got a current that's doing that too, following it. Okay? In theory. So what's happening here, and this is I find this one of the hardest things to teach. What's happening here is this magnetic field, as that voltage rises, is building up in one direction. Imagine it expanding like a balloon. Right, that's the best way I think of describing it. Until it hits a peak, and then starts to collapse away like a balloon expiring. And this is the hardest bit to get. It then expands in the opposite direction, so north and south poles reversed, and then it collapses. All the time that's changing, there's a relative difference. There's a change in magnetic field. And therefore that coil and the conductors in that winding are experiencing that change in magnetic field cutting across the inductors. So we get an induced voltage in that coil. Yeah. But remember what we said, Lenz's law says that induced voltage will oppose the change in current that's causing it to happen. Just going to look ahead here a minute. Yeah. So what we get in this circuit is when we got a current rising in that direction, yeah, we get an induced voltage across here. So if that's plus at this moment in time and that's minus, we get an induced voltage here that's trying to force current back in that direction by induced. Yeah. What that does is, if the current's trying to rise this quickly, it slows it down, pushes it back. It's never big enough to stop it actually going up, but it holds back. It makes the current in the circuit lag the voltage that's causing it. Okay? Do you get that? Kind of understanding it or not? Yeah? What that means is, going on the next slide, is if we had a pure inductor, a coil of wire that had no resistance but just inductance, can't get that practically because even a bit of wire's got some resistance. But if we did, what we'd get is a current and a voltage that were 90 degrees out of phase with each other. Yeah, that's what I've tried to draw in that little diagram up the top there. The blue line is the applied voltage. Okay? As that rises, the current in the circuit's rising. We get a big, it's rising at its fastest, remembering our stuff from calculus, the slope of this, the rate of change of voltage is biggest where it crosses zero. That slope is the biggest. Therefore, we get the biggest induced EMF and the smallest current. Here, it's not changing at all. What it causes is this current here, the red one, to be 90 degrees behind or lagging the voltage we're applying. If we draw a phasor diagram of that, remember phasor diagrams from complex numbers. Here's our applied voltage there, VL. We're talking about angles going round anti-clockwise, and our current here is 90 degrees behind it. So when the applied voltage is at a positive or negative peak, the rate of change of flux to 0. So when we're at the top here, that flux is not changing. No change in flux. No current induced. When the applied voltage crosses 0, the rate of change is at maximum. So there is that point. There is where rate of change is maximum. That's where you get the maximum current induced. So for a pure inductor, current lags the voltage by 90 degrees. Alright? We're going to come back to this again in AC theory as well. We're going to look at what capacitors do in AC circuits as well then. When the voltage is changing, you've got an induced current. When the voltage isn't changing, which is at the peak point, that peak at the instant, there is no current. So it causes the current in the circuit to lag 90 degrees behind the voltage. This is a theoretical thing because, like I say, you can't get just an inductor with no resistance. It's not possible, is it? Because you make an inductor by coiling wire up, and wire's got resistance. Alright? Yeah? So everybody happy with that? So, the inductive reactance of a coil. So if this phenomenon of induced voltage and current is going to hold back current in a circuit, that's an opposition to current flow. It's called the inductive reactance of that inductor. XL is the symbol used, X being for reactance, L meaning for inductive reactance. Later on we're going to be talking about capacitive reactance as well, XC. Right? And it's measured in the same as other opposition to current flow things. It's measured in ohms. So we now got three things measured in ohms. We've got resistance, we've got impedance, and we've got inductive reactance. Because the induced EMF and current will be greater if the applied voltage changes faster, the magnitude of inductive reactance is dependent on the frequency of the applied AC voltage. If we put the hertz up, that voltage is going to be changing quicker, and therefore we're going to get more induced current, and therefore more inductive reactance. The formula for XL, inductive reactance in ohms, is 2 pi times FL, where the F is the frequency in hertz, and L is the inductance of the coil in henries. We'll also be looking where we find XL from equal to omega L. And that's just the omega part is the 2 pi F bit of that formula. So there's a switch over, and we will at some point be using both. Alright? So what that means is that formula is that XL is a frequency dependent quantity, and it will vary if we change frequency. And we put frequency up, XL gets bigger, frequency down, XL will go down. So we can determine the inductive current from the applied voltage divided by XL. Right? Everyone happy? So Ohm's law still applies, but you're going to find out in AC theory eventually some complex number math comes in there. Alright? Everyone happy? No questions? Good. Right. So, our experiment was not this imaginary inductance only coil. It was a coil that had some resistance. So, a real coil can never be a pure inductor because the wire of the coil will have DC resistance. So a real coil can be represented in a circuit by putting a small resistor in series with the inductor. So we've got the inductor's got a capacitive reactance XL, and the wire has got some DC resistance R. And that symbol represents, as a representation of a real inductor. Our real inductor here. Yeah? The resistance of the inductor does not change with frequency, but reactance does. This leads to a different term being used to describe the opposition to current flow in an AC circuit. We call it impedance, symbol Z. And it's also measured in ohms. Note, for DC current, frequency F is equal to 0, and hence XL will be equal to 0 ohms. There is no inductance with a DC current because it ain't changing. Okay? But it is why you get this transient period where the voltage you apply has risen from 0 to 10 volts. Okay? That's the subject of later on the course, and even more so in electrical principles in year 3, because we look at transient periods. Alright? So you're all happy that that's a way we could represent this coil as a resistor in series with a pure inductor. Yep. So, what we then do is we draw a phasor diagram representing the 3 different ohmic values: resistance, reactance, inductive in this case, and the impedance Z. We can create an impedance triangle or impedance phasor diagram where your resistance is the in-phase component, the one with no angle associated with it, because it doesn't vary. That's fixed, so we fix that along the horizontal line left to right. And then our inductive reactance is 90 degrees, and inductive reactance is 90 degrees upwards. Then if we resolve that triangle created there from a parallelogram, our impedance Z is the value up the hypotenuse there. Okay? And then eventually we'll be, in AC theory, we'll be wanting to know what this angle is in here. So we got that as a complex number, polar form. Yeah, because we got, soon as you've got phasors out of phase with each other, you've either got, if you're going to do maths with it, you've got to usually use either polar or rectangular complex form to do that. Alright? So we got on it. This is often called the in-phase component and the out-of-phase component. Yeah. That's the reason that is up there is what causes that's how much the impedance is ahead of the resistance that will cause the current down here at the same angle. Again, that's later on, Lewis, but that will come back to that. But we can find the impedance of this phasor through Pythagoras' theorem. So the square on the hypotenuse is equal to the sum of the square on the other two sides. So that's that formula there. Pythagoras' theorem, you should all be familiar with that, yeah? So, this is what happens in regards to impedance changing with frequency. If we have no frequency, i.e. DC, left-hand diagram, there is no reactance, R and Z are in line with each other, the Z and R are equal to each other. Yep. No. No, you get a slight lag, you get slight things if there's a transient, a change in voltage level, but that'll alter for a period of time and then settle back to a new steady state. Yeah? If we have a low frequency, XL is relatively small, okay? Resistance doesn't change with frequency, and we get a phasor with a smallish angle. If we increase the frequency, resistance still doesn't change, but XL gets bigger, increasing this angle and making that line longer. Has to. So as we put frequency up, the impedance of an inductor increases. You all understand that? Can you see why that happens in terms of the phasor diagram? So what's going to happen to the current? If impedance gets bigger, what's going to happen to the current in the circuit? Down. Right? And I'm going to emphasize it again now. This is a science lesson. Understand the electrical theory behind it and don't get too hooked up in maths. Yeah? In an inductor, if you increase frequency, the impedance is going to go up. Therefore, Ohm's law says the current will go down, because we can have an AC version of Ohm's law that says IAC is equal to VAC divided by Z, the impedance. Yeah. Still Ohm's law, but this value changes with frequency. We don't get that in DC circuits. Alright? All happy about that? So, guys, so what we're going to do now then is use that phasor diagram and the results we got from the experiment up front to determine what the inductance of that coil is in henries. Yep. So, what we need from this is, have we got a resistance value for that coil on the front page? 7.1 ohms. Yeah. We haven't got an XL value. We can't measure that, right? Is that the resistance that came from passing DC current? This one down here. 5.6 ohms is the one we want. Right. I'll try the one with the ohm meter. I can't explain why. We're at 5.6 ohms. Because that's what was the resistance to that DC current, yeah? So R, 5.6 ohms. What other value we got on the front there that we measured? We haven't got XL. We got the impedance. Z we measured, or from our experimental values, was 11 ohms. Yeah? So they're the values from experiment. What can we do with those values? Z squared. Let's write the formula down, Lewis. Start with the formula and then rearrange it.
So you got Z equal
Z
to
is equal to R2 squared. Yep. Yeah. Yeah, so I can write XL squared is equal to Z squared minus R squared. Yeah. And square root both sides. Yeah. So we got XL is equal to root Z squared minus R squared. That is root 11 squared minus 5.6 squared equals. Now write what we usually put, square both sides. Subtract R squared square root both sides. That's the process of rearranging that. So what's the answer? 9.47. So 9.5. Onions, biscuits, bourbons, ohms. So we've got an XL equal to 9.5 ohms. How can I turn that don't know anyone in Wakefield. Go away. Up north. Up by Leeds. Get a brew on. Right. I don't. Too many people other than you guys have got to listen to it. Right. Down there. Right, guys. So how can we turn that into inductance L in henries? WL. Omega. Yeah, but do we know what omega is, Jack? Have we got a value for that? Yeah, okay, so omega XL is equal to omega L is equal to 2 pi FL. Frequency 50 Hertz. Because that's mains, that's going to be within about 0.0 something percent of that in this country, I would think. Certainly within 0.5%, 50 Hertz. Can we do it now? Yeah. Because we can rearrange XL is equal to 2 pi FL by dividing by 2 pi F, all in one go. So you get L is equal to XL over 2 pi F. That's 9.5 over 2 pi times 50 equals some millihenries. Because we've got to find the inductance of the coil, Jake. Now we found the inductive reactance, yeah? Now we use the inductive reactance we've found to find the inductance in henries, which is what coils are specified in. Well, you had it in maths, yeah, because where we've done questions with complex numbers, and you did a circuit. We're going to go back and revisit that in a more scientific way. To that then, guys, 0.03 henries or 30 millihenries. Yeah? Alright? So we used the theory about the difference between DC resistance and AC impedance and phasor diagrams to do an experiment and determine the inductance of a coil. Alright, and also around that I use that to explain why try and explain why we get less current in a coil when we connect it to AC than when we connect it to DC. There's a point that I can bring from industry, right? We used to have some machines, and you know little plug-in relays you get with multi-pins on the bottom. Some of them got 8 pins, some of them got 10, right? That machine had some relays in there with 24 volt AC coils and some with 24 volt DC coils. Yeah? And if you measured the DC resistance of the AC coil, it's about 2 or 3 ohms. And if you measured the DC coil, about 50 ohms. Right, and we had this situation where this blinking relay kept burning out. People took one out, put a new one in. Oh, that's an AC relay. Put that back in there. Carry on, burn out again. Someone look at it. Oh, AC. Put another AC one in. What it weren't doing, it should have been a DC one. Right? If you put the DC one in the AC circuit, it won't work. Too high resistance, too high impedance. Put the AC one in a DC, it will work for a period of time. That period of time depends on how often and how long it's being energized for. Because you're going to get a really high current flow because of its low DC resistance. But if that's only flicking on for a couple of seconds every 10 minutes, it's going to last ages. The person's going to come along and they're going to look at it and they're going to change like for like. It's only when someone really look into why this thing's happened time and time again, they find out that someone's fitted the wrong relay. So you'll always find that, but that's the difference between those two coils. You might think they look exactly the same outwardly. You couldn't tell the difference other than looking at the writing on them. And the natural thing is to go and get from the stores what you've got in your hand, isn't it? So just be careful, I think, is what I'm saying. All right. So that's today's kind of theory bit.